Okay, this is a worked example for a quadratic model to do with a ball being thrown from the top of a building. So let's have a look. A soft ball, why it's soft, I don't know, is thrown upwards from the top of a building. The height h meters of the ball above the ground after t seconds is modeled by this function. H of t equals h plus 9.8 t minus 4.9 t squared. If you've covered it in kinematics, you might think this looks a little bit like one of the Suvat equations. Okay, we'll not worry about that at the moment. I mean, it's essentially what it is. First of all, what does the constant h indicate in the function? Okay, so um, well, we've got that down here. Part A, when t equals 0, h0 is equal to h. I mean, these t terms fall out. So it's the initial height. Okay, I think that should probably say t greater than equal to 0. But that is the initial height when t equals 0. Okay, so that is that bit. At what time is the ball the same height as when it was thrown? So we can imagine this being thrown up from the top of a building. It's going to go down and sort of by the side of the building and just drop down on the ground below. And that's, I think, is the idea behind the whole thing. But of course, if you throw it up in the air, then at some point it's going to kind of pass the level where the thrower is stood. So that is what it is asking. So up here, part B, it is at height h when, okay, well, we can just put that h in there, that actual value in for the variable h. We've got this equation. Well, the h's drop out, of course, and we can factorize to give us this. And that gives us two solutions, actually. T equals 0, which is the starting condition. But I think what they are looking for is this t equals 2. So it's come, after 2 seconds, it's come back down to that point from which, the same height as from which it's been thrown. So it is at the same height when t equals 2. Part C, now I put this in here, it wasn't in the original question, but this is kind of fairly typical of these kind of quadratic models of questions, so I thought it was actually worth doing. What is the maximum height of the ball in terms of h, and after how many seconds does it reach that height? So if we look at this function again, we can rearrange this, and this is the normal thing that we do in these sort of quadratic models, in order to be able to complete the square. So we've now got it in this form. Looks a bit ugly because we've got this h unknown here, which makes it a bit more cumbersome. But yeah, so it's basically looking like this. So that expression is the same as that. Okay, so if you don't know how to complete the square, there are other videos on that, but you can expand that out for yourself if you like, and just check back to the original form of the expression. Now, the maximum is going to happen when t is equal to 1, because we see this term here. If it's not equal to 1, then this is going to be some positive number, and its overall effect, because of this negative sign, is going to reduce the height. So so if it's slightly more than 1 or slightly less than 1, it's going to be not at the maximum, and the maximum will occur when this component is 0. Okay, it's squared, so it's always going to be positive. So so whether it's positive or negative, the square of it is going to be positive. Okay, so that will be the point in time when the ball is at its maximum. Interestingly, half of that, I think that's probably what we would expect, isn't it? And that actual maximum, if we substitute t equals 1 in there, then the actual height is given by this times this. There we go, minus 4.9 times this lot, which is equal to h plus 4.9. So it's 4.9 above the height of the building. Right, so that's that part, and this sort of analysis here is very typical of these kind of quadratic models. Most of these quadratic models are negative quadratics like this one, because the x squared or t squared term or whatever is negative, and therefore the graph is a kind of a parabola that goes with has a maximum. And sometimes they're to do with maximizing profits or all sorts of things. But this one is height. Okay, so part D, find in terms of h how long it takes for the ball to first hit the ground. That means before it starts bouncing. And so, when h equals 0, the ball hits the ground, and so we can substitute 0 into our quadratic here. Well, I've skipped ahead, and because it suits us to actually to use this expression here. So this is the same thing. And therefore, if we can knock out the minus 4.9, just divide through by minus 4.9, and we've got t minus 1 squared equals equals this. And take square roots, we've got plus 1, t minus 1 is the square root of 1 plus h over 4.9, and therefore t equals 1 plus or minus the square root of 1 plus h over 4.9. Now, this is going to be greater than 1. So if we were to take the negative solution, we have negative t, so that's not what we're looking for. So we're looking for the positive solution, which will be the positive sign, which is this. Well, it's expressed in terms of h. So if we don't know the height of the building, then we don't know what t is. But and it might tell us that and ask us to evaluate it in other questions. That's the sort of thing that you might get. This one is slightly more obscure. It says, how much longer does it take? Does a ball launch from 25 meters, stay in the air, compared to a ball from 15 meters? Now, from that, I think we can reasonably assume that what they want is the difference between the two. I mean, a comparison is a bit of a subjective thing, isn't it? A bit of a narrative thing. But this is the difference that we're going to calculate. And so what we're going to do is we're going to evaluate the time for a 25-meter building and for a 15-meter building, and subtract one from the other. And of course, in order to do that, we can just substitute our 25 in for h there, 15 for there, work this through, and it's going to come to 0.455 seconds to 3 decimal places. So that is that. So a nice multi-part quadratic model. And just to emphasize, this treatment of the quadratic function to actually identify the maximum in the case of a negative quadratic, or it would be the minimum if it was a positive quadratic. But in this case, this treatment of completing the square is a very useful way. And note, actually, you might be tempted to use your calculator in other circumstances. In this one, we don't know h, so we couldn't do that anyway. So completing square like this is our only option on this one. Okay, so hopefully you found that useful, and I'll see you next time.